probability. And also, the questions that I gave you here on this review for 7 and 8 are a little bit different than the ones in the quiz. So if you wanted to like do the quiz over to kind of practice, they're different questions. Only a little bit, though. I just changed the numbers. So we have Jan, and Jan is a member of a class with 35 students that meets 5 days per week. A student in the class is randomly selected to explain how to solve a homework problem, that's super scary, every day of the week. And once a student has been selected, I should say he or she, is not selected again in that week. So if Jan was not one of the 4 people picked earlier in the week, what is the chances that she will be picked on Friday? So first of all, figure out, this is kind of, she would be 1 person picked. How many people are there left to pick from if somebody isn't chosen again?
31.
There are 31 people left. Do you see what I'm saying? Because, okay, so there were originally 35. Okay, and you picked somebody on Monday, they can't be chosen again. You pick somebody on Tuesday, they can't be chosen again. Somebody on Wednesday, they can't be chosen again. Somebody on Thursday, and they can't be chosen again. Which leaves you 31 people you can pick from. Does that make sense? Okay. So the probability that Jan on Friday, she's how many of those 31 people? She's one of them, assuming no multiple personality things. 1 out of 31.
Well, even multiple personality.
Yeah, I know. It would be the same person. I'm just being sort of trying to be funny and failing. So, if it was being picked on Monday, what would the probability have been? 1/35. Tuesday would have been 1/34. Okay. Alrighty. So casino games often use a fair die that has 6 sides with 1 to 6 dots on them. When the die is tossed or rolled, each of the 6 sides is equally likely to land face up. We do not have a loaded die. Using the physical assumption that the die is fair, find the probability of each of the following outcomes for the number of dots showing on top after a single roll of a die. So it's kind of like you play a game and you win if you get a 1 or a 5. So what's the chances you're going to get a 1 or a 5? Probability of 1 or 5 is 2 out of 6 or a third. You don't have to make your fractions in decimals. Like, you can leave 1/3 as 1/3. It's fine. How about an even number of dots? What does that correspond to? Probability of getting an even would be 3 out of 6 or a half. And just to be specific, that would include getting a 2, a 4, or a 6, right? Those 3 things. Okay. So that's not super bad, is it? Okay. Let's see if I can do this without turning the page like all cattywampus. Okay. Suppose a student is asked to choose a number from 1 to 10. Define A to be the event that the student chooses the number 7, and B to be the event the student chooses an even number. Okay, so let's actually list the stuff in A. So A is the event that you choose the number 7. How many things are in that event? 1, and it's just 7. Okay. B is the event that they choose an even number. Between 1 and 10, how many even numbers are there? 5, and what are they?
2, 4, 6, 8.
Okay, great. Okay, no, okay. What is the probability of A and B? 0.
Yeah, it would be A or B.
Yes, exactly. A and B is 0. That's saying you picked a 7 and you picked a 2, 4, 6, 8, or 10. That is not possible. So that is an impossible one. You cannot pick a number that's 7 and is even. No go. If I'd asked P of A or B, what would that have been? 6/10. So you have to be really careful. In mathematics, language is really precise. Like and or mean different things, right? So be really careful with that. A and B is an example of an impossible event. Another way to check that the probability is going to be 0 for an and is if you take these 2 sets and you intersect them, like look for where they overlap. If they have no overlap, That's called the empty set, and its probability is 0. Do you know what I mean by overlap? They have nothing in common, right? If I had said A was the student chooses the number 8, just for pretend, what would P of A and B have been? 1/10. Does that make sense? So if, for example, A had been, just hypothetically, 8, if you look at the things that are in A and B, there's just one of them, right? 1/10. One thing that's both 8 and even. Okay. Are the events A and B independent? Explain how you know. Now, the best way to check for independence is to use this P of A and B equals P of A times P of B. If that's true, they're independent. If it's not true, they're not independent. They're dependent. Okay, so presuming you know P of A and B is equal to 0, right? Okay. How about P of A times P of B? So probability of A, chances you pick a 7 would be 1/10. Chances you pick an even is 5/10 or 1/2. Multiplies to make 1/20. And so since P of A and B not equal to P of A, P of B, events are either not independent or are dependent. And I guess dependent is less writing, so.
So when it says explain how you know, we have to use numbers.
Yeah, explain using numbers, like using, and in this case, the explanation is, do you know how to use this mathematical formula to check for independence? That really is the best and easiest way. Yep. Okay, are the events mutually exclusive? Explain how you know. So this one actually really is not very hard to check. Two events are mutually exclusive if they don't contain any of the same things. They have no overlap. So A and B are, I'm just going to capitalize that ME, if they have no simple events in common. Is that true in this case? Yes. This is true for our A and B. So the answer, I guess, is yes. So yes, they're mutually exclusive because they do not contain any of the same events. Okay. I had one poor soul last semester who was in my Calculus 1 class and was in my Stats class, and this question was in honor of her, although her name wasn't Julie. So, suppose this person is taking Calculus and Statistics, and suppose at the outside of the term, probability for getting A's in both classes are as follows. A in Calculus is 0.3, A in Statistics is 0.7, and an A in both is 0.2. Are these events independent? Explain how you know. So how could you check?
Probability of both them.
Yep. So let's call this first thing, let's call that event A, if that's okay? And let's call that event B, just so we can like shorten the names. Does that make sense? Okay. So we know P of A and B, don't we? Like they told us what that was, right? What is it equal to?
0.2.
0.2. And could you find P of A times P of B? Which equals? Oh, so close. Barely, yep. Since P of A and B not equal to P of A, P of B, these events are dependent. Okay. That is one thing I think I did better this year than the previous time I taught statistics, is that this really is the way to check for independence. It is much easier than trying to think like, oh, does this thing affect that thing? I don't know. Okay. Now, the probability that she will get at least one A. So, yeah, you have to interpret that this is actually an or. At least one A means an A in the first class, an A in the second, or an A in both. Does that make sense? So we really want to find P of A or B. Now, is this just P of A plus P of B? No, what do you have to also have there? Subtracting. And I think the diagram is the best way to think about that. Like if you have your events in A and your events in B, P of A finds all that stuff, right? Which counts the middle part where they overlap, right? P of B finds this stuff, right? And that middle stuff has been counted twice. That's why you have to have this whole taking away thing. What if the A and B don't overlap? Do you think is it any different?
You don't need the and.
You don't need the whole and part, but even if you had it there, is there anything in the and?
No.
This would just be 0, right?
Yeah.
So, I mean, anyhow. So I don't know what this rule is called, like it's like rule 3B or something, like 3A, I don't remember the number, but there's all those rules in section 7.4, write those down. I think actually a really good thing to do would be to write the rule down on your note card, and then write down an example of the rule being applied. Does that make sense? Like write the rule down and put an example below it so you kind of see it in use, as opposed to just this abstract thing and you're like, numbers, letters, what do they correspond to? I think it helps to have rule, find an example of it, and then have that in your notes. It'd be much more useful than just random stuff.
Where in the book did you see it?
I think this is section 7.4. So you can go back and look at your notes, all those rules were in boxes. I think it's rule 3A or something, but I can't remember what number specifically.
Did not have all the rules summarized at the end of that chapter?
It probably does. Yeah, I'm sure it does. But you could just flip through your notes and look for stuff in boxes. And
Yeah.
so what's P of A? Sorry, kind of got sidetracked there. It was 0.3. P of B was?
0.7.
And if you forgot the second thing, it's 100% chance of getting 1A, right? Minus 0.2. 0.2,
Yeah.
which I think works out to be 0.8. Okay. Because students totally use random number generators, right? I bet you could ask Siri or any other, I don't know about phones because I don't have one, but I bet you could ask something like Siri to find your random number between 1 and 10. Probably would do it for you, right? Probably. Siri will do calculus for you. You say, find the integral of blah, and it'll do it.
Roll the dice for you.
Yeah, that too, which is kind of like random number thing, right? Okay, so 2 students use a random number generator to pick an integer between 1 and 20. What is the probability they pick the same number? Probability of the same would be the first person picks 1, so it'd be 1 over 20 times 1 over. Actually, that's not right. No, this is, my notes are wrong. Hold on a second. I need to use the whiteout because I can't use my eraser. Okay, let's think about this way because I boo-booed. So first, let's find the total number of combinations. You know what I mean by that? So how many numbers can be chosen first? 20. How many can be chosen for the next spot? 20, which is a total of 400. Does that make sense? Okay. Now, of those 400, how many are the same? Well, that would be picking 1, 1, 2, 2, 3, 3, 4, 4, etc. How many of there are there? There are 20 of them. So, for example, things like 1, 1, 2, 2, etc. Up to 20, comma, 20. So that's 20 out of 400, which reduces to 2 out of 40 or 1/20th. Okay, how about probability of not same, picking different numbers? What rule is that officially using? Complement rule, yep. So probability of not same would be 1 minus probability of same, 1 minus 1/20th or 19/20ths. So that's an example of the complement rule. And I think that one is the easiest to understand, right? But it is the trickiest to see its applications. Do you agree with that? Because anyhow, stuff like this next one. Suppose the probability of winning a casino game is 0.15 and it's independent from one game to the next. If you play the game 10 times, what's the chances you win at least once? So this means you could win once, twice, 3 times, 4, 5, 6, 7, 8, 9, or 10 times, right? All those different combinations. Which is the opposite of what? The opposite of winning never. Does that make sense?
The opposite of the probability they get on it.
Exactly. So this, you have to recognize that this thing really is a complement. And that's the best way to do it because, oh my God, if you win 2 games, you could win the first 2. You could not win the first one, the next 2, right? There's lots of ways you could win 2 games, right? That's, oh my gosh, and then we win 3 games. Like, it's so much crap. So, what is the probability that you never win? 0.85, but you play the game 10 times at 0.85 to the 10th. So 0.85 is not winning once, right? But 10 independent times, that'd be 0.85, 0.85, 0.85, 10 times. That comes out to be 0.197. So probability that you win at least one is equal to what? 1 minus that, which is 0.803. One of the most common things done on the quiz was people said 0.15 to the 10th, which is some ridiculously small number. What is that 0.15 to the 10th actually finding? It's you win 10 times, right? As opposed, that's what that is finding. And so that's not what the question is asking you about, right? Okay, so that's wrong. Alrighty, next thing. So this one, I thought, on the quiz, I said you could use a table or a tree. I think I'll do it both ways, just to show you both methods, because the table, I think, is a bit harder to figure out, but it makes part B a lot easier, and the tree is easier to figure out, but it makes B a bit harder, okay? So let's just go through both methods. Oops, I definitely prefer black. Okay, so we have this whole 2% of individuals that undergo a medical test have a disease that the test is intending to identify. That might not be big enough boxes. Okay. So we have the yes disease, no disease. And then we have the positive test, negative test. You can structure your table in a different way than me. As in, you could have disease be in the rows or vice versa. It doesn't matter. But what kind of matters is what you fill in first. So the whole hypothetical 100,000 means you start with a pretend total of 100,000 people. Okay. What is the first thing that you are told?
2% of people have.
Only 2% of people have the disease. So would I be filling in the totals down here
Yeah.
or on the sides?
Down there.
Down there. Does that make sense? Because this would be the total people who have the disease, right? It's the total who don't. If I had put the disease right here, then it would be the end. It just, there's no like perfect way to do it. So 2% of people have the disease, so I take this 100,000 and multiply it by 0.02. And you get 2,000. And goodness, once you know that, can you fill in the next box?
2,000.
It's 2,000, I think. Am I right? Am I wrong?
Oh, yeah, I never mind, I did 20%.
Am I right? Okay. How about
98,000.
98,000? How did she find that?
Minus 2,000.
You could do 100,000 minus 2,000, right? I'm afraid, like, when I did this the first time on my own notes, like, I didn't subtract correctly, and I got, like, a wrong answer, and I was like, what's wrong with me? So I would actually use your calculator to check you, because, like, you know, subtraction is difficult.
Don't do 0.2.
Now, the next thing you know is that if you have the disease, the chances the test is going to find it correctly is 0.99. So which box is being filled in by that?
Yes, positive.
Yes, and positive test, yep. So you take the 2,000 people and 0.99, that proportion of them are found correctly. That is 1,980. And then once you know that, what other part can be filled in? The negative test, which is 20. Okay, if an individual does not have the disease, the probability that the test falsely gives a positive result is 0.05. So which part of the box gets filled in by that? Positive test and no disease. So 98,000 times 0.05, 5% of them are going to get a positive test result. That's 4,900. Making this next box 93,100. And the totals are 6,880 and 93,120. If you do it this way, the thing I'm checking for is you have these numbers right. Okay, like those four things in the middle, really. Okay, so using that, let's do part B, then we'll go back and do the tree. So if the test result for an individual is positive, what is the probability this individual actually has the disease? This is a conditional probability. What we're finding here is the probability of disease given a positive test. And the whole given a positive test bit means you're in the positive test row. So in the positive test row, how many people actually had the disease? 1980. Out of how many that took a positive got a positive test? 6880. And it's 0.288 is what I got. So the kicker in this question is that it's not likely you actually had the disease in the first place, right? Okay. So that's the it's the table way. I'm gonna make a new slide for the tree. So you ready for tree? Okay. End slide. There we go. Okay. So in your tree, the first branch you make is either you have the disease or you do not have the disease. Kind of like in the table, that's the first thing we figured out as well, wasn't it? Yeah. Okay. So what's the chances you have the disease? 2%, so 0.02. 2, right, as a probability, which making the probability for no disease is 0.98. Great. And once you're in both categories, you could have the disease and get a positive test, right? So positive test, and that happens probability 0.99, right? What's the chances that you have a negative test? 0.05. Oh, no, 0.01. If you're in the diseased category, that is. Okay, for no disease, positive test, negative test. Which of those branches do you, or which label was given to you in the problem? 0.05 goes in the upper or lower branch?
Positive test.
Oh, no, oh, you're right, it does. Yeah, no disease, you're right, it is upper. I don't know what I was thinking for a second there. Yep. And negative test happens in probability. And then you multiply along the like paths, like this times this times that, right? And what that's going to tell you is probability of disease and positive test is 0.0198. This one is disease and negative test, that's 0.0002. This one gives you 0.049, and this one gives you 0.931. And so if you're doing the tree, I'm checking that you have all these numbers right. What should they add up to? 1. And actually within the groups, notice how the first two add to 0.2, right? The 2%. These next two add to 0.98, which is the proportion who don't have the disease, right? Okay. So I think the tree is intuitively easier in the beginning. Do you guys agree with that than the table? Okay, so if you like the tree, go with it. Now the question is, how do you do the whole disease given positive test? And remember how this whole P of A given B was equal to P of A and B over P of B? Does that ring a bell? Okay, so this is P of disease and positive test. It has to be scaled to the people who had a positive test. The ends of the branches don't give you all the information. You do have to use this rule, okay? So what's the chances of having the disease and a positive test? Which of those numbers is that? 0.0198. Do you guys agree with that? Okay. Now the kicker with the positive test is the positive test could have happened in 2 different ways. Either you had a positive test and you had the disease, right? Or you have a positive test and you don't have the disease, right? So what numbers have to go on the bottom?
0.0198
Plus
0.9.
0.9. Does that make sense? So the thing really there is that probability of a positive test is the same thing as probability of disease and positive plus probability of disease and negative. That's what this part is tricky. Because think about it, either you have, if you have a, oops, I wrote the wrong thing, that's why I got the confused face. That should say disease and. What am I saying?
No disease.
Disease and positive, no disease and positive, yep. Yeah, so either you, when you have a positive test, either you have it or you don't, right? Those are the 2 categories. And this should be the same number we got from the previous calculation. So most of you who did the tree, unfortunately, you missed this part. Does that make sense? Okay. Awesome. All right, chapter 8, random variables. So give an example of a variable that is discrete. which means only sort of
Number of cats you
number of cats you own. I'm so sorry.
It's okay.
Number of cats you own. The kicker is you only can own whole numbers of cats, and the possibilities for but it has to be a thing that's actually changing, right? You can't just say 3 cats, because that doesn't change. No, it doesn't vary. Number of classes you've skipped, number of days you've slept in, I don't know, something like that.
What if you had a cat with 3 legs?
It's still a whole cat.
Still a whole-
It's still a whole kitty.
Disabled people are whole people.
Yep, disabled pets are whole pets. Somebody always asks that question, it's so cute. Okay, continuous. Weight of a cat, yep. Weight of kitty. Oh, I just wrote cat with a K, oh my gosh.
Wait, a girl named Cat.
Weight of a girl named Cat, yeah.
Continuous.
It would still be continuous, yes, it would, okay, all right. Anyway, you get the idea. All right. Suppose this probability distribution for x equals number of jobs held during this past year for students at a school is as follows. What has to be true about the numbers, assuming I've given you all the possibilities, what has to be true of these numbers? They have to add up to 1. Okay. So find the probability that x is bigger than or equal to 3 and explain what it means. So that is the probability that x is equal to 3 plus the chances that x is equal to 4. Does that make sense? Okay, so that's 0.15 plus 0.06 is, So this is the probability a student had 3 or 4 jobs is 0.21.
In this,
You don't have to say 3 or 4. You could have said 3 or more, that's also correct.
or like at least 3.
This would be, at least 3 jobs is also correct, yep, because that means 3 or more, yep. There are lots of ways to say this correctly, and as long as your statement is equivalent and correct, it's fine. Like, I was pretty flexible on that. Okay. Find the probability that a randomly selected student had 1 or 2. Probability x equals 1 or x equals 2. And actually, the reason you can use this rule, just px equals 1 plus px equals 2, is that those are disjoint events, right? There's nothing in common. They're mutually exclusive, sorry. You can't have... This is just in the number they held. So you either held, I guess they're looking at the highest number only. Okay, so what's that? What numbers would you add there? 0.43 plus 0.21 works out to be 0.64. Okay, how about P of x less than 3? No, does the fact that there's no or equal to matter for this thing?
Yeah.
Yes, it does. This is a tricky thing. For discrete variables, it matters when you have an or equal to. But for continuous stuff, it doesn't, because the area of a line isn't 1, is 0, is what I meant to say. So which would this add up? It'd probably x is equal to...
Could we just subtract 1 minus?
0.15.
Because it's the complement of A.
I think it is the yes, I think it is the complement of A. Do you guys agree with that statement? Either you add up the probability that x is 0, 1, or 2, right? Or you could do 1 minus the answer to A, that's the same thing. Yep. So I did it the long way. I got 0.15 plus 0.43 plus 0.21 is 0. Which is the same thing as 1 minus 0.21, right? This is the probability a student had less than 3 jobs, right? No.
So, would the answer, 79% of students had less than 3 jobs be wrong?
Nope.
Okay.
Nope, that's fine. Okay. And this cumulative probability distribution function, so this thing, what it does is it sort of finds the probabilities that you're less than or equal to a specific number. So this is number of jobs less than or equal to whatever number we're given. And the probability. So like with 0 is the probability that you've had less than or equal to 0 jobs. So what's that probability? 0.15. When you look at 1, it's like saying, what's the chances you had 1 job or less? 0.58. How did people get that?
You added 0.
You added 0 and 1. Exactly. It sort of accumulates the probabilities. For 2, what's the chances you had less than or equal to 2 jobs? That's 7, 9, yep. 3 jobs, 0.9, 4, and then 4 jobs, 1. The last one's always 1, and the first one is always the same as your first value, right? But you just sort of accumulate one probability at a time. Okay. So I've been meaning to bring this in. I told you that I had a great story about how some MIT kids cheated a casino game, right? So they used expected values to do so. And I want to show you that, but I have to figure out how to make it into something you understand, because it makes my eyes spin a little bit when I read the book, because it's a little bit like, I think I'll help make like a little worksheet out of it, but it's a pretty fun story. Suppose you play a game where the following table gives probability distribution for X, which is the number of wins in 3 independent plays for the game, where the chance of winning for each game is 0.3. This officially is a binomial variable. You don't actually have to use that here, but it is.
Because you either win or you don't.
Yeah, exactly. So the n is equal to 0.3. Oh, sorry, yes, the n is 3. Sorry, you're right. What's the probability of success? 0.3. And also, binomials do require that your trials are independent, but I think we're told that, right? Yeah, 3 independent plays. Okay. So we can do this expected value, we'll do it 2 ways, actually, because there's 2 ways we can get this. If it wasn't binomial, you'd have to use this formula, which is E of X is equal to a sum of your X's times your probabilities, is the official formula. So for example, what's your first X? 0 wins, and its probability is 343, exactly. Your next X is 1, its probability is then 2 times 0.189, 3 times 0.027, that comes out to be 0.9. And that formula is very general and works even if you don't have a probability like a situation that's binomial, okay? But because this is binomial, so because binomial, there was a general formula for that, and it was E of X equaled NP. So that's 3 times 0.3, which is 0.9. I think the best way to think about why this works is to think about a coin toss. Because you can visualize coin toss. Suppose you tossed a coin, n equals 200 times. How many heads do you expect to get? 100, roughly 100, right? Notice how that is 200 times 0.5, right? Roughly speaking, you're going to expect to get 100 on average, right? That's not always going to happen, but that's what you expect on average. Same kind of idea, except for this is just harder to visualize than a coin toss, right? Okay. Calculate the standard deviation. So I'll show you the really general way, and also the shortcut because you have a binomial, okay? So the general way, first you find sigma squared. Is that the standard deviation? That's the variance. So once you get your answer, what do you have to do to it?
Square root.
Square root it. And the general formula is a sum of xi minus mu squared times pi. And that mu, or mean, that is the expected value. It's the same thing. I don't know why they had to give it two names, but it is common. Okay, so that's going to equal, so my first x value is 0 minus 0.343 squared times its minus 0.9, yes, I got ahead of myself. And I was testing you. 0.343.
I love pens.
I'm sorry.
I know, right?
Which is why I recommend against their use.
I can't. Pens.
I know, it smears. They make erasable pens.
Yeah, okay.
They work really well too.
I think they're okay. They do. They've gotten a lot better. There's certain kinds that have gotten quite a bit better. 1 minus 0.9 squared times probability of 441, yep. And then you keep going, right? You got 2 minus 0.9 squared, right? Times 0.189. I'm just going to erase my other little thing. And what's the last bit? Okay, and that comes out to be exactly 0.63. So regular sigma is the root of that, which is 0.891 approximately.
You want us to always go like 3 decimal places?
I'll be very careful to specify on the test. Or, because binomial, sigma is root np1 minus p. You can use that formula too, but only in the case that it's a binomial random variable. And it's pretty easy to prove you get the same root 0.63. So this is root, your n is 3, your p is 0.3, right? And what's your 1 minus p? 0.7. And if you multiply those, you end up with, well, 0.3 times 0.7 is 0.21. 0.21 times 3 is 0.63, which is you'll get the same result out of it. I didn't really realize you could do it this way until a whole bunch of you in your quiz were smarter than me and did it this way. And I was like, wow, that was clever. So this is actually faster if you recognize it, but if I give you a situation that's not binomial, you have to also know how to do that. Does that make sense? Okay. So write a short sentence explaining the meaning of the expected value in this situation. So there's a couple important things you have to say here. You have to kind of clarify that this is like a long run average. Does that idea make sense? So over the long run, you will win 0.9 games, and I was picky if you didn't say out of 3. Say on average. Do you see that the out of 3 actually is important? And that was kind of essential in all of our calculations that we made, right? So I'm looking for something about a long run average and the whole, you get that the out of 3 matters, because out of 4 would be a different expected value.
You win less than 1 game.
Yes, on apps, this is a bad game to play, right? What the gamed the lottery system figured out is the tickets cost them $2, and when they calculated the expected value of a ticket, it was $5. And so they were like, holy crap, if we buy lots of tickets, and they bought like 20,000 tickets, they would, over the long run, come out ahead. And they ended up quitting their jobs, and playing this lottery game.
Can you still do that?
No, the lottery went defunct. And then the lottery got smart. I don't understand how the lottery, like in Massachusetts, which contains like MIT and other technical schools, lots of really smart people at them, made a lottery where they didn't like check this out, but they also restricted the number of tickets you could buy. And so if they cap the number of tickets, you can't use the whole long run average of expected value to come out ahead.
Unless you buy like the max tickets at each place.
But it was like, but you really did do it, you had to really buy a lot of tickets, like hundreds of thousands of it, and like even their max was not high enough for that to pay off. Remember we talked about distributions? There's too much variability. They want to get to the case where they have that super tight thing, where they don't have much variability, and then they can weather their losses. So, smart kids. Okay, suppose we have a treatment for a disease, and when it's applied to a random patient, the probability they recover is 0.7, and we're going to apply this treatment to 5 patients. Let X equal the number of patients who recover. Find probabilities for the following events. So we're assuming that X is binomial. So how do we know this, and what are we assuming that we didn't mention? So first of all, how can you tell it's binomial? Yeah, there's 2 outcomes, right? So there's 2 outcomes. Do you see how that's kind of that's where the bi comes from in binomial? Recover or not. And the thing that we assume, this was actually told to us in the previous problem, but I didn't actually say it here. They have to be independent, yep. So we assume independence. So for example, you should not apply this drug to a pair of siblings because that will affect the probability that the drug is successful because they might have characteristics that make them more likely to be in the success group or the fail group.
Does it matter that they have the same probability across each trial for binomial? Or?
Yes.
Okay.
Yeah, that's kind of what the independence gives you. Yep. Okay, and this formula, remember, this can go on a note card, obviously, but Px equals K was n factorial over K factorial n minus K factorial P to the K 1 minus P to the n minus K. I have that memorized, but I think you guys should probably write it down. In this case, what is our n? 5, because we apply the treatment to 5 patients. What is the chance of success, assuming success is you get better? 0.7, great. And I will once again show you how to simplify factorial, so if your factorial button or your calculator is not so nice to you, you can deal with that. So find the probability that exactly 3 individuals recover. So that's P of X equals 3. So what does that 3 tell you? What does that go in for? K. Okay, so we have 5 factorial over 3 factorial. 5 2 factorial, yep. P, which is 0.7 to the power of 3. And then 0.3 to the power of 2. And think about it, we have 5 trials, right? The success was 0.7, right? You have 3 0.7s multiplied. Set 0.7, 0.7, 0.7. Those are your three successes. And then the 0.3 times 0.3 are your 2 failures, right? This thing just counts the ways you can arrange them in that list. Like either having the 3 successes first, the failures last, or mixing them all up. Okay, now factorials. So remember 5 factorial is 5, 4, 3, 2, 1. 3 factorial is 3, 2, 1. And 2 factorial is 2 times 1. Oops. And so look at those factorials. What cancels? The 3, 2, 1s do. And you have 5 times 4 over 2. So 5 times 4 is 20. Over 2 makes 10. So just go ahead and put, this is 10. And then all of a sudden, maybe I'm crazy. Well, okay, I am crazy. But I think putting this in your calculator and doing that little bit of algebra first is easier than putting this thing in your calculator. Having to go find that stupid factorial button, right? Okay, and then you put on your test, if you have spare time, go back and check it using the factorial button. You should get 0.3087. Did you miss it or did you get it?
I finally got it.
Okay. It's just- Okay. Is that all right?
Do you want us to round that to 0.30?
I promise I'll specify in your test, okay? I absolutely promise I will be explicit about how you should round because that happens all the time. I just was lazy and didn't do it here. Okay. 2 or more. Now, I'm going to show you 2 ways to do this. We're going to decide which one is better, okay? So this is really probability that x is bigger than or equal to 2, right? Which means you have to find that probability x equals 2, plus probability that x equals 3, plus probability that x equals 4, and don't shoot me now, probability x equals 5. Which means you have to redo the thing we just did 3 times, right? 'Cause, yeah, okay. Or, what else could you do? Complement. You could use probability x is bigger than or equal to 2, is 1 minus, be very careful. What should I put inside that p thing? You can do it 2 ways, either less than 2, or you could say less than or equal to 1, couldn't you? But less than 2 is fine. So if less than 2 people recover, that means either no one recovers, it's a sad day, right? Or another sort of pretty sad day is only 1 person recovers, right? So it's easier and faster to use complementing for that thing. Does that make sense? Okay. So now let's work out what px equals 0 is. And this won't be very, very hard. And we'll work out what px, well, then we'll plug the answers in. So that's 5 factorial over 0 factorial times 5 factorial. 0.7, what's that powered to? 0. And 0.3 to the power of 5. Did you guys? At 0.3 to the 5th, which should make sense because if no one recovers, that's 5 failures in a row, which is 0.3, 0.3, 0.3, 0.3, 0.3, right? Also, what the special thing I use there is that 0 factorial is 1, which is just what it's defined to be. Don't try to ask why, just accept it and move on with your lives. That comes out to be 0.00243. Then x equals 1 is not so bad. That's 5 factorial over 0.7 to the first, 0.3 to the fourth. And just think about that. It's 5, 4, 3, 2, 1 over 4, 3, 2, 1. So it cancels to 5. So I have 5 times 0.7, 0.3 to the fourth, which comes out to be 0.02835. So your final answer is 1 minus those things added. And try to be like modestly neat with your work. Like, I have to remember that I feel a little bit sorry for me. I do have to grade 60 tests, and the messier you are, the crankier I get. Don't make me cranky. Some students have a severe aversion to like the left side of the page. Like they start writing their work on the right side. I don't understand why they don't like the left side. You get 0.96922. I'll tell you how to run your test, I absolutely swear.
If you forget, do we get cookies?
Sure. I got my calculus kids cookies. I could get you cookies too. But it took me like 2 weeks to get them cookies because I forgot to get them. Then I forgot them in my car for like a week. And yeah, so anyhow. Cookies are okay. Well, if you don't mind the fact that I might be a ditz and forget for a while, then we're good to go. Okay, find the probabilities for the x is the pulse rate of marathon runners, for which the mean is 60 and the standard deviation is 5. Assume a normal distribution. So this is the thing where we're using those fancy table things, the z-score things. Oh yeah, so I'll have some extras, but you can use that on your test in addition to a note sheet. Okay, so I'm not gonna make you like somehow cram that table onto a note sheet, absolutely not. So first, just on the side, find the z-score and just be modestly neat. So z is x minus mu over sigma. This is not the fancy thing from chapter 9 here, it's just plain old values. So what's the x that I'm given? The mu is, and the sigma is, okay. That comes out to be minus 2.2. And that's your work. So this probability is equal to the probability that z is less than or equal to negative 2.2. So you look at your table, tell me what you get there. You're in the negative part of it.
0.0139.
0.0139. Great. Okay, x is bigger than 62. First thing you should do is find your z thing, right? You can do that first, or you can do what you're kind of motioning, which is like flip it around first, right? Do you see what the flipping around is coming from? This goes the wrong direction, but I'm just going to find z first. So z is 62 minus 60 over 5. What does that come out to be?
2/5.
2/5, which is 0.4. Great.
Do you want us to put our work in? You're like, I've just been putting a star button.
As long as your work is just legible, it's just some people were so messy, they just like mixed it all up. It's just kind of like put off to the side, like a little bit. You just have like some organizational structure. Okay. Now, your tables only do one direction. They do less than. So you have to use your whole complementy thing here. So that will be 1 minus. And with these variables, the whole equal to doesn't matter as much, really at all. 1 minus, you should get for this part, you get 0.6554, which is 0.3446. Just the whole fact that you got a complement makes sense. Okay, and part C is meant to be helpful because I gave you the same numbers as an A and B, right? So that's the same thing as probability that Z is in between negative 2.2 and 0.4, right? And I really think a visualization picture is pretty helpful for this. You have, there's your 0, maybe there's 0.4, here's negative 2.2, and you're looking for the area under this curve. So you find the area from 0.4 all the way down, which is this, right? What do you take away then? So kind of what I did there is I found the area from here, including this little bitty tail. Subtract the itty bitty tail, exactly. So minus p z less than or equal to negative 2.2. And if you pull them from the right places, you already found these numbers. What is this first number? Is it this point, is it the 0.3 thing or is it the 0.6 thing? 0.6. The 0.6 thing. 0.6554. And then how about the other one? 139, right? Which comes out to be 0.3307.